brief preview yesterday that they were looking at translations between logic, the inheritance hierarchy, which is a tree of formalizations into a heavily interconnected grid.
The rest of the
I've seen Ambrose have already taught you, or is assuming that you know, category theory. Only need very mild category theory, and if you don't know anything, it's fine. But we're going to introduce the notion of theory more. You've heard of morphisms maybe before. They're well known as translations between models, theories. Then you've heard of group homomorphism before. Here we're going to look at morphisms between theories. So we're going to translate from one theory to another. And since our theories represent formal systems, we will use these theory morphisms to represent translations from one formal system to another. So they're basically mapping the syntax of one system to the syntax of the next. So in the end, the theory morphism has to map all expressions of the source theory to expressions of the target theory. So S and T are theories, and our morphism is going to map everything that S has, like every syntax, context, types, expressions, and so on, to corresponding syntax over T. It's going to have degrees of freedom only for the symbols. So we're going to define M for S symbols. And for all other syntax, we're going to use homomorphic extension, meaning we keep the syntax tree as it is. We just swap out the S symbols for the expressions that we map. Theory morphisms are important because they have some extremely nice properties. In particular, the induced mapping of expressions from S to T preserves all the judgments. So everything we had in S, like every typing, every equality, every provability is preserved, is still true over T. So we can use theory morphisms to not just to translate, but to translate in a truth-preserving way. We're guaranteed that all theorems that we had in S will still be true in T. And that's extremely important when you're building large networks, large formalizations, where you need to transport stuff from one area of your library to another. And then you want to find M only for the small number of primitive symbols of S, and get induced a large number of translations for all the definitions that you already have in S. And remember, the definitions are theorems, so all the theorems of S get translated to theorem. So as a concrete example for LF, remember, LF theories are type constants or kinded constants. We map the type constants to a type term, and M of C, that's the expression that we're giving for C, has to have translated type, where this is the homomorphic extension. Similarly, we check the kind to the homomorphic extension, and then that's what our expression M of A that we're providing has to satisfy. So for all the named symbols, M and C and M and A are just given. So that's also our degrees of freedom. And then the rest is induced. This is the homomorphic extension. Everything gets mapped basically to itself. Type goes to type, variables to themselves. Lambdas go to lambdas. We just recursively translate all the sub-expressions. Pies goes to pies the same way. Application goes to application. So we're really just pushing the morphism M through. The only interesting stuff happens at the leaves when M of C and M of A are given by the morphism M itself. So we just keep the syntax tree unchanged, just swap out at the leaves for the symbol references the expression that we're mapping it to. So some more nice properties. We only have to give finitely many of these. So our morphisms are finitely presented translations. Moreover, these, if our base language has decidable typing, like in the case of LF, these are also decidable. That means it's decidable whether a morphism is well formed. We have a relatively compact finite presentation. We can implement a checker for it, and it gives us a total translation of the syntax that preserves all the judgment. So MMT generalizes this. Instead of just doing it for LF, it does it in general. So recall MMT theories are just lists of symbol declarations. Expressions are just constants, variables, and these complex terms, which do binding and application, typing and equality judgment. And now morphisms are defined the same way. For every S symbol, we need a definition that respects the translated typing. Morphisms are again defined homomorphically, and now we can prove at the MMT level once and for all the good properties of morphisms, in particular that they preserve all judgment. So this kind of theory morphisms you can define for every formal system. Usually it's not done. If you read a paper, usually won't find the definition of theory morphism. I think that's because they're not needed for anything else. Like you can't cut out substitution because somewhere in your presentation you're going to need substitution. You can't cut out your typing judgments. They're going to come up eventually. But theory morphisms happen to be so advanced that you can cut them out without losing much. You only need them when you scale up your library. And in a typical research paper, you don't do that. So you don't need to talk about theory. That's why many people aren't even aware of it. And that's why many people don't even bother defining them, which is a shame because theory morphisms are also a great sanity check for your system. If you cannot easily define a natural definition of theory morphism, then you've probably done something wrong in your system design, for instance. Because every nicely designed system usually admits theory morphisms in a very straightforward way, and because of that, we can define them generically at the LF level for every logic formalized in LF. And even more generally, we can define them generically at the MMT level, every kind of language that could be implemented in it. That's the main theoretical result about MMT seen as a formal system. A little bit of history. The earliest and most systematic study was in the area of algebraic specification. There's a community of people mostly looking at first order like logics. They don't do lambda binding so much, but they could. It's just community of different priorities. The development graphs, late 90s, kind of then made the jump to proof assistance. The Isabelle locales were inspired by development graphs. That's maybe how most of you have come into contact with theory morphisms before. PVS has them. I added them to 12, and then MMT in a way is based on the idea of doing stuff so generally, but still specifically enough that theory morphisms can. And you can use them very nicely for modular development. You can use them to model inheritance. You can use them to model implementing interfaces. The concept is always that the domain theory represents what you need, like your axiomatization, your specification. And then the morphism implements or defines everything that the specification requires in terms of some other language. So if you're giving an implementation of a specification, this is the specification, this is the programming language, this is the implementation. If you're giving a mathematical model of some theory, this is the theory, this is the model, and this is mathematics. But always a translation of everything from the specification to the realization environment. And because theory morphisms preserve truth, we are guaranteed that we are correctly modeling on. This, I think I will skip until tomorrow, and it's the so I've taken the very basic propositions from yesterday again. I think it was Monday already. And simplest possible formal system, just conjunction, just the syntax of conjunction. And now we are going to map that to the syntax of disjunction. And I'm going to need negation as well. Maybe you can already guess where this is going. The morphism is going to be the Morgan translation. Keyword in MMT for morphisms is view. If we state them at top level, you can think of it with viewing disjunction logic as an instance of conjunction logic. How do we do it? These are definitions. The left-hand side is the symbol from the source theory. So this prop is the prop of conjunction logic. The right-hand side is the expression from target language, which in this case happens to be prop as well, but this is now the prop of disjunction logic. So it looks more trivial than it is. Then conjunction has type prop, prop, prop. We need to translate the type. In this case, it's easy because prop goes to itself. So we still have prop to prop to prop. And then that's what we have to check this against. And this is indeed a function. So we have expressed the Morgan translation of conjunction into disjunction as a theory. Let's look at a more complicated example. These are the official propositions from the atlas that I showed yesterday. That's the official equality from before, for example, untyped equality with natural reduction roots. And here I already have a morphism. Use a different keyword because this morphism is now written in a slightly different way. It's written inside the theory, meaning it goes from here to the containing theory. I could equivalently close this theory up here and then give a view untyped equality is an equivalence, and then I'm going from equivalence congruence into untyped equality. So I map everything from equivalence congruence to untyped equality. I have to first show you equivalence congruence. That's here in the file relations. Just the very simplest self-contained formalization of common relations. We have things that just have a type, so just the carrier. We have a binary relation on it, carrier to carrier to type, just some judgment, not even any logic involved, just using LF's type for the judgment. Reflexivity, then I write the relation as infix dollar. And then reflexivity, symmetry, transitivity, that's all as usual. And then I can define things like a pre-order, an equivalence, a congruence, or something that's an equivalence and does substitution. And eventually I get equivalence congruence as the theory of binary relations that are equivalent and preserved by substitution. And then I can here prove that my formalization of untyped equality is indeed an equivalence congruence. The carrier goes to term, because I have a relation on terms now. The binary relation is now take two terms and give me the judgment that they're provably equal. Now I have to prove reflexivity. That's easy because I have explicitly axiomatized reflexivity up here. I have to prove symmetry, which is a relatively straightforward proof. Same for transitivity. And I have to prove the substitution property, which is again easy because I've axiomatized it explicitly up here. So it's a relatively easy proof of the equivalence properties of equality. But what you can do now is you can prove other equivalence congruences. For example, in propositional logic, we have, where is it? The equivalence connective, just prop to prop to prop. And we can also give a morphism here. This time we map carrier to prop. So now we need a binary relation on propositions. So we map two propositions, x, y, to the judgment that they are provably equivalent. So this rel now has type prop to prop to prop, which works. Prop to type, because we have mapped carrier to prop. Now again, I have to prove that my equivalence relation is reflexive and symmetric and transitive. Those are slightly more complicated proofs because that's not something we usually axiomatize. For equivalence, instead, we have the introduction elimination rules that I have to apply. The benefit of this now is anything I have proved generically here for an everything I've proved generically where I'm going. Oh, those two files. Everything I've proved generically for an arbitrary equivalence congruence can be carried over. So for example, here I've proved transitivity for 3 elements, very basic lemma about transitive relations. And that can now be carried over if I want to use transitivity of 3 elements for the equivalence predicate. I just say equivalence, that's the name of the morphism, applied to transitivity 3, and then that is going to have the appropriate type that I can do it before it was called transitivity of the equivalence predicate for 4 elements. And here it then has type something like if x y and so on. And I can use the same operator for quality. Just now I use the morphism equivalence, I use the morphism EQ, and now trans4 has the type x equal. So in this example, I'm not gaining much because all I'm carrying over is the proof of these transitivity helpers, but this applies for anything I have proved here. So that's the main advantage, kind of like when you do object-oriented programming or in Isabelle locales, if you have seen that before. You axiomatize the thing you want to talk about in the weakest possible setting, like with the weakest possible set of axioms. Then you do the proof. Then you do a morphism into the concrete setting in which you want to apply the theorem, and you can carry over the proof. So then you quickly end up with, like we already have this inheritance hierarchy of theories. Every theorem is positioned as far to the root as possible, meaning with as few imports as possible. And then whenever you do some other formalization, if you notice that some point of the hierarchy can be imported, you give the appropriate morphism and you carry over all this. Everything we did yesterday, and now we can apply that to logic transactions. Any questions on that? So for logic translations, we do basically the same thing, except of course our theories are more complex. Instead of going from something very simple like equivalence relations or just conjunction, we start with a complete logic like standard first order logic or propositional logic. and we translate that somewhere else. But I'm going to actually use it as part of a more general application. In particular, a little preview, I'm going to merge the semantics of a logic with the notion of logical settings. Just if you think about it, what is semantics? If you think of the inductive interpretation function that you know from textbooks, that also has a very similar flavor. It goes inductively over the syntax and translates to something else, to the meaning. So what we're actually going to see is that semantics and logic translations are kind of the same thing. The main thing why they're different, in my understanding nowadays, is more of a philosophical question, namely between the formalist treatment and the Platonic treatment. So usually, when you look at individual researchers, you will have strict separation. You have the formalists who basically do theorem provers, proof systems, logical frameworks. They just take their formal system, they take their implementation of that system, and they start typing, and the stuff they build in the system, those are the actual objects of interest. So in particular in LF, initially nothing exists. Things only come into existence by declaring them in our LF theory. So it's like we start with nothing and we build the objects that we want to work with. The Platonists, on the other hand, which includes pretty much all the math, approach things from a different angle. They're saying, well, the world of mathematical objects already exists, and we're just discovering them. We're just writing informal narrative descriptions that identify or point to the objects that already exist in the Platonic. And I think that's actually one of the main reasons why proof systems and formalized mathematics haven't taken off so much. Because the math that actually exists is Platonic. And when we formalize things, we're doing it in a formalist framework that leads to a culture clash. And we find out that a lot of the stuff that the mathematicians don't bother spelling out, we have to make precise and formal in the formalist setting. The mathematicians don't have to spell it out because they're assuming things anyway exist in the Platonic realm. They just have to write enough so that other people can find the objects themselves. In the formalist setting, the objects don't exist unless we define them exactly. So we have to do a lot of different work in the formalist setting. So what does formalist semantics of a logic usually consist of, or what does Platonic logic usually consist of? We assume we have a category of theories, theory morphisms, but not necessarily as defined in LF, just any theories whatsoever. So many modern theoretical or Platonic approaches to logic are perfectly fine with having uncountably many theories or uncountably many formulas, these kind of things. You know, maybe you've seen infinitary conjunction before, maybe you get a conjunction of infinitely many formulas. All of these things happen because we're just saying, some abstract category of theories, and then some set of expressions and formulas for every theory. Doesn't really matter what the set is. Could be the category of all sets or something. Then we have a class of models for everything. And we have the inductive interpretation function, which takes a theory and a model and it interprets every expression of the theory in the model. And in particular, all the sentences somehow go to truth values, and then if they go to truth value 1, we consider them true in the model. And we usually say if they're true in all models, then those formulas are theorems. And if we additionally have a proof category around, we can define soundness and completeness as saying that we have a proof whenever it's true in all models and the other way. And what I started doing some 20 years ago when I started my PhD is talk to people from both sides of this adjective border, and I try to make sense of it and try to combine them in the logical framework approach. I'm going to try to summarize how well that went. So main slogans to remember if you are drifting off during this part of the lecture. We've already seen a logic is just a theory in the logical framework, of course, and maybe there are some constraints. So for example, if we say it's any theory whatsoever, we don't even know what the propositions are, and we might want to know what the propositions are. So maybe we say something, it should inherit from our theory of logic so that we at least know what the proposition is. And the logic translation is going to be just a theory morphism. And of course, again, maybe there are some constraints, but the basic idea is logics are defined as theories as the framework, and then the translations are theory morphisms. And semantics is going to be just a special case of a logic translation. The difference will be purely pragmatic in the sense that instead of translating from logic 1 to logic 2, we're translating from logic 1 to a formalization of whatever we consider the ambient semantic language. Could be set of C set theory, or it could be the calculus of constructions, or it could be a programming language. Whatever we decide to believe in as a faithful representation of the Platonic world that we want to work with, we formalize that itself as an LF theory. Here we're jumping from the Platonic to the formalist world. Take whatever we think of the Platonic world to be, formalize that once, like we do in all the proof systems. And then we can just think of semantics as translations between those. And then we can define soundness and completeness once and for all. With sound, if the morphism that translates the syntax to its meaning also translates all the proofs. If it does, because theory morphisms preserve all expressions, that means if we had a proof here, we have a proof here, that's soundness. And the more complicated property, completeness, means that the morphism is conservative. Basically means if the type was empty before, the morphism is going to map it to an empty type as well. So if we had a formula that didn't have a proof here, after mapping it over, it still doesn't. That's conservativity, and that ends up being equivalent to the semantics being good. And that also nicely shows why soundness and completeness are so difficult, not so differently difficult to practice. If you look at the typical textbook definitions, they kind of look like duals, right? There's two sides of the same equivalence. Implication is opposite direction. But soundness is always easy to prove, and completeness is always hard. And this is the reason soundness just goes in the direction of the morphism. So all we have to do is extend the morphism to all the translated proofs, and we're done. It's a straightforward induction. Completeness goes against the morphism. If we have an expression here, then we must have had one here already. But this language is stronger than this one, because if we're able to translate, we can express everything of the source language in the target language. Target language must be somehow stronger or more expressive. So because this is a stronger language, it's much harder to reason the other way around. If something exists in the stronger language, it also exists in the weaker language. That's a hard proof. And it's one of the annoyances that so far I've been unable to come up with some kind of recipe how to prove completeness at the logical framework level. I can define it, but it doesn't help with doing any of the completeness proofs. So this formalist Platonic distinction is orthogonal to the proof theory model theory distinction. But in practice, what we see is that if people do proof theory, they're usually formalists, and if they do model theory, they're at least more likely to be that. That's why these communities have been mostly disjoint. Getting better, of course, the better proof systems become, the more interesting they become also for the Platonists. And the more the formalists and the Platonists talk to each other, the more the formalists realize that our formal systems are ridiculously insufficient to actually cover the richness of mathematics. So that creates challenges, so we improve our formal system. We're progressing, but there's still a big gap. The proof theoretical approach, often we consider a logic done if we have syntax in proofs. And we don't even bother about defining what the models are. Some people say if your definition of proofs is good enough, if your theorem proof is good enough, you don't need models to begin with. In the model theory setting, the abstract models are often the main object of interest. It's about specifying properties and then studying the class of models. They're much more interested in the models and the interpretation functions between them. If you don't know what institutions are, look it up. It's a very nice model theoretical framework that captures a lot of these abstract ideas in a very nice way. And the work I did in LF basically connects LF to institutions. I'm not going to talk about that now. So the next couple of slides, I'm first going to show you a couple of slides where I start with the formalist definition. Those are the ones we've seen so far. Formalist definition of logic as a theory in LF. And then try to derive things from them that connect to the intuitions that the Platonists already have. And then we do the opposite, start with the objects that the Platonists work with, and formalize those in LF. In particular, formalize the semantic ambient theory, formalize the interpretation functions, formalize this part first. Basically what I've said before, but now made precise. We're defining a logic to consist of an LF theory L, a distinguished type of propositions, and a distinguished type family of proofs for those. That's the absolute minimum we need to reasonably call it a logic in the sense that we have formulas and truths of formulas. Otherwise, well, we might have a type theory, but if we don't have any statements that can be true or false, it gets pretty boring. So we need something that collects all the things that can be true or false, and then something that tells us which of them are actually true and which are false. And in Latin, that's very easy. Prop and det are exactly what the theory logic defines. So we just need to inherit from logic. And we can say all the theories that inherit from logic, those are the logics. Now we define the objects that come with logics. And L theory is just an extension of L. So let's say L is first order logic. Then our sigma is a particular theory of first order logic. It declares a couple of function symbols, a couple of predicate symbols, a couple of axioms. Or if L is high order logic, then sigma has to do things like declare a couple of base types, declare a couple of typed constants, and again declare some axioms. So there's still some degrees of freedom in exactly what declarations we're allowing, but for now the easiest thing to say is that all of these extensions where we just add some declarations to the logic, those are our theories. A sentence over the sigma theory of logic L is then just a term of type prop. And the proof of F is a term of type data. I also define disproofs that comes in handy if you're formalizing logics very generally. Sometimes there are logics where proofs and disproofs have their own separate inference systems. So we also define disproofs using this negation trick.
Does having a system for these proofs help with the completeness proofs? Like,
depends on how good your system of disproofs is. So the logical framework doesn't make it substantially easier. It just helps you organize your thoughts. So for example, in the non-monotonic reasoning community, it gets really complicated, and they do a lot of work with proofs and disproofs and trying to meet in the middle. But generally, disproofs are harder and they don't magically solve anything. And we can define what a theorem is or a contradiction. It is a proof or a disproof. And of course, to avoid any confusion, most formulas will be neither. Like some formulas have proofs, some have disproof. And then there's a lot in between, which has. Now, given such a logic, we can get category of theories. The morphisms in this theory are just the morphisms between the extensions. So let's say I have a logic. I have signature 1 and theory 2. And L morphism between these is now a theory morphism down here, which is the identity on L. So it maps everything of L to itself, and all the non-logical symbols that come from sigma 1 map to whatever we have in sigma. That way, if this is first order logic, then we do actually get the usual definition of first order theories and first order theory morphisms. Skip the rest. That's the big up on later. Now logic translations. Let's say we have two of these logics. I'm going to use an unprimed and a primed one. We have to define what the translation is. It's going to be a theory morphism from L to L prime. So if I have my prime here, I need a theory morphism T up here. That's going to be my logic translation. Now, what should the constraints be? We could require that we map prop to prop prime. Most obvious, most natural thing to come up with at first. If you want to preserve the structure, so propositions of L should go to propositions of L prime. But that turns out to be too restrictive. So what I'm doing instead is I'm saying, okay, propositions can go to anything. So prop prime doesn't have to be the same as T of prop. But we need to be able to lift our translated propositions from the result of the translation to prop. So I have my L propositions. I apply the translation T. I'm going to end up in some other type. I apply the term tau to it, and that gets me a prop prime term in your proposition of the target. So to get the formula translation, then I just have to compose the translation T, which is a homomorphism, with this final step tau, which maps everything into the target type prop prime. And then I require that proofs go to proofs. So the det symbol has to go to something defined in terms of the det prime symbol. And then the tau has to be in here, which in particular means the tau can be uniquely obtained from the morphism. So this will become clear if we look at examples. It's just going to be a challenge to show all the things that we need parallel. Let's do the classical propositional logic to intuitionistic propositional logic. I think that's the most obvious part. Have you seen that translation before? Does the term double negation translation ring a bell? Yeah, so the basic idea is this is classical propositional logic, and this is intuitionistic logic. Basic idea is we translate all the connectives to themselves, but we stick a double negation at the top. So every formula gets double negated, and that maps it from the classical logic to the. This double negation happens once at the top, so that's why we need this truth lifting tau, which is just the double negation. So then proofs of F, this is not supposed to be a comma. Proofs of F get mapped to proofs of not translation. And in our case, T is almost the identity, it depends a bit. There's different variants of the translation. Sometimes you stick a couple extra double negations in certain places. But for propositional logic, it actually works if T is the identity, except for mapping that F to that of none. Let's look at this in action. Really wish we had more black points. First, our logic is built, propositional logic is built by taking propositions and proofs, and then we have things like negation, implication, and so on. And eventually we're merging everything again intuitionistic propositional logic. And then we have some module of being classical. And if we merge that in addition, we get classical propositional. This column. Now our morphism is supposed to go you see green on green? Yeah? Our morphism is supposed to go from classical propositional logic to intuitionistic propositional logic. We're going to define it in using the same modularity as the source language. It's a very common thing. Since we have to inductively translate everything from the source theory, we can follow the same modularity as the source theory had. So CPL starts by working with propositions and proofs. That's what we translate first. Propositions go to themselves, and the proofs of F go to proofs of not F. And now we look at all the other modules. For example, the module of being classical now has to go, well, it can't go to just classical if we don't have that in the target. In the target, we need at least negation. We include this one, and we map the axiom of being classical the proofs get really annoying with all the double negations, a lot of negation, introduction, negation, elimination that we have to do, but they all work. In order to show you this a bit better, I'm going to duplicate the diagram. It's a bit confusing because source and target language share the same modules. Let's duplicate everything. Then we have CPL here. IPL sits here. Also prop proofs, negation, this. And now our morphism basically has to go all over. So all the various modules have to be translated to IPL. In the end, it's sufficient to go here. We can use all the material from IPL. But in practice, it turns out we can go to weaker logics and then rely on the inclusion to map it to IPL. So for example, to express classicality, all we really need is negation on the other side. So classicality can go just negation. And conjunction has to go, this conjunction goes to conjunction and negation. So we have conjunction here. Conjunction here. And this one goes over to basically where the unions used to. And then since all of these are ultimately included into atomistic propositional logic, any subset of the module is sufficient to be an intuitionistic. We could even break it down further because as it turns out, every rule only needs itself. So to translate and introduction, the only thing we need on the other hand, on the other side is and introduction and negation, introduction, negation, elimination. Similarly, the left elimination of in conjunction only really needs left elimination of conjunction. So by spelling out exactly the requirements I have on the target side, I'm maximizing the ability to reuse the morphism thing. Right? So the domain, the source of the morphism is always the specification. The more I have, the harder it gets. Like the more states I include here, the more I have to map, the more proof obligations I have. Whereas the codomain, the target theory, is what I'm using to do it. So here, the more I have, the easier it gets to the proofs. But then the reuse potential is limited. Because if I want to compose this morphism with something else, the smaller the codomain, the likelier the chance that I can find something else to keep translating. So we always try to make this one as big as we can to translate as much as we can, and make this one as small as we can to do the representation theorem in the weakest possible. So then you can also read this as a meta theorem that says, in a language in which we have conjunction and negation, and in which we are translating proofs and formulas according to the double negation translation, we can express conjunction in the following. So this includes here. I haven't shown you that because I was hoping I comes kind of intuitive from the example. This is an include between two morphisms. So this is including this morphism from up here. And it's again a copy paste intuition. So all the assignments from this morphism just get copied over into this one. And categorically speaking, that has the following effect. I want to delete this, okay? If we have some theory S, which is included into some theory T, and we're giving the morphism M into some other theory U, we have two options. We can take everything that T has, including the stuff inherited from S, and map them individually. Or, if we already have a morphism from S, we can just include that one. That's basically saying, map all the stuff inherited from S according to this existing morphism, and we only map the rest. And then occasionally it happens that the target language has some similar modular structure, where this morphism goes into something else that's included into U. Then including this one just means we get the composition. So, but that's incidental. So really, what officially happens is we already have a morphism from the included theory into the target, and we include that one. And let's go back to some examples that are easier. This is the example I showed at the very beginning. Just conjunction to disjunction. No double negation or anything, very straightforward, the Morgan. But here I did it by explicitly mapping prop to prop. Prop was inherited from conjunction logic, and I had to map it. And alternatively, I could once and for all give the identity morphism from propositions to propositions, which maps prop to prop. And I can just include that morphism here. I don't actually gain much time here. The boilerplate is arguably too much, but it's because the example is so trivial that this happens to be a trivial morphism that I'm including, but it shows you the basic idea. I can just, if I have an existing morphism or something that my domain includes, I can just include it. In programming language terms, this is a side note now, this is basically delegation. If you think of the entire morphism as an instance of this class, like implementing this interface, then we're basically saying this interface inherits some other interface, and for all methods from that inherited interface, we're delegating to this existing object that we already have. So now, of course, writing the identity morphism is stupid. Like, we don't need to manually write the identity morphism. And indeed, the way we can just do it is we can just include propositions. If we include the theory in a morphism, it's not really a theory, it's just a shorthand notation for the identity morphism of that. So that's why if we find include the theory name in here, that just means everything from propositions goes to itself. So that's the scenario where I have some theory S here, and it's included. That's just logic. And it's included into both sigma 1 and sigma 2. If I give a morphism down here, typically I'm going to start by saying include L, which means for L, we're doing the identity. And then we only have to map the stuff from sigma 1 suppose there's a C coordinate in here. Then we would have a C maps to here. So includes the identity of L. The logic goes to itself, and then we just map the rest. The pedagogical upshot of these include declarations is that we're guaranteed that this diagram commutes. If you don't know what that means, think of it as this way. The diagram is a graph in which the nodes are the theories and the morphisms are the edges. And commutation means if we have two paths from one node to another, they're all equal. So here we have two paths from here to here. We can go this way, or we can go this way. If the diagram commutes, those have to be equal. That means if we take anything from L and we map it to here, it's the same as mapping it here and going here. In this particular case, they're both the identity, because L is included here, mapped to itself here. It's just included. So yeah, both come. So by including explicitly in morphisms, we can tell the framework that certain rectangles and triangles are supposed to commute by construction, which means the framework can then leverage that. MMT maintains the entire graph of theories and theory morphisms, and it uses the diagram chase, meaning the reasoning on equality of paths, to conclude that certain ways to go from one theory to another are the same. And that's extremely helpful with large-scale libraries where it's not as easy anymore as in these examples, where you chain morphisms in one direction and you have the inheritance hierarchy in the other direction. Then you can very quickly get some very complicated morphisms with some non-trivial notions of commuting diagram. And of course, in general, not every diagram commutes. But we could have two different translations from one logic to another. And that happens all the time. So only certain subdiagrams commute. So it's very important to know which ones. So I've shown you the logic translation. A good exercise to try to extend that. And you do disjunction to disjunction and negation. Try to map the or introduction or elimination words and so on. So that if we copy paste this, replace the word conjunction everywhere by disjunction, and then try to do these things. They're relatively easy, but still can take you an hour or so if you're not logic or framework literally. But it's very good practice to see what's going on. And it's changed so much. What the framework does is it tells us the computed types. For example, in introduction rule, we know it goes proof of F, proof of G, to proof of F and G. But now we're translating all proofs to proofs of double negation. So our proof obligation here is given a proof of not F and a proof of not G, we have to give a proof of not F and G. So then P is going to be the proof of not F, Q is the proof of not G, and here we have then the proof of not F, E is a proof of not F, negation introduction gives us a contradiction. We started originally with not introduction, so that includes the proof. Okay, in the middle we have another negation contradiction proof to get not G. So it always gets quite messy. So typically there's two nestings of not elimination and not introduction corresponding to the two layers of negation that we have on Rabe. And the challenge is always to figure out which formula to pick for the contradiction proof. So we need E not G on the inside and the not F on the outside, and then combine. So all of this compiled, it's just I've made so many live chains. This. Let's look at a different, or any questions on double negation. So I only put the conjunction example here in the full atlas. There is the entire translation. For first order logic, it gets a bit more complicated. You have to stick an extra double negation in front of the body of the universal quantifier. So for all cannot go to itself, it has to go, for all F has to go to for all not F. But then it works out again. But if you Google double negation translation, there's all kinds of different variants. Basically, if you stick double negation in enough places, eventually it's going to work. I just picked the one that has the least amount. But then, for example, what I never bothered to write is the double negation translation for the typed quantifiers. I've only done it for the untyped case. And then I should also have to write it for the soft typed case. But yesterday I told you how quickly the number of theories can explode if we cover all the different cases, all the different combinations of base language features. But then the work gets even worse when we do these morphisms. If we have 8 different versions of the quantifiers, chances are the kind of translations work for all of them, so then we have to do 8 different translations. And yeah, that's like only for untyped first order. What's the easiest? Next example, maybe modal logic. So, who knows modal logic? Let's quickly show that also. Hold up for modal logic here. Very simple. Box is a logical feature of propositional logic, the unary operator of propositions. So it's the diamond, and we get modal logic by taking propositional logic and box and diamond. That dropped the proof theory here from the beginner's version of the atlas. In modal logic, this is usually read as necessarily true, and this is read as possibly true. And then it allows to reason about like degrees of truth or degrees of confidence or different beliefs of limitations. There is a well-known way to translate that to first order logic, and the idea is that we, doesn't matter if it's first or higher logic here, I think higher logic, we basically write one theory of crypto frames in which we have one type of the worlds and a binary relation on worlds, usually called accessibility relation. And with that in place, we can then translate modal logic to this theory of the crypto frame. Translation looks like this. Gives you to digest while I draw a new picture. model logic arises by including propositional logic, block, diamond. And on the other side, could have, for example, first order logic or higher logic, doesn't really matter, except I'm using the type variant here. So I'm also including all the various features. In particular, propositional logic is included here. And then I extend that to build a theory of first order logic, which declares the W and the accessibility relation. And then I give a morphism that maps the entirety of model logic. And again, I could do this modularly. I could give individual morphisms from here, from box, from diamond. Just here for compactness and putting everything in a single morphism which starts here and which maps all the stuff that's included in one morphism. Proof theory, I didn't have the sanity check on how to say things. So if you've ever heard of crypto models, that's exactly what these represent. So you put every formula in every one of the set of worlds. So now our propositions no longer get mapped to propositions, but to indexed propositions, meaning one truth value for every world. And then the truth lifting is the universal quantifier, which says, okay, proofs of formula F go to proofs that the translation of F is true in all worlds. Probably use a W for the variable to be. So provability in the model logic goes then to truth in all worlds. And this in all worlds, that's a top level step of the translation where we have to stick a for all in front. Just like for the double negation translation, we have to stick a double negation at the top. Here we stick a for all. And now all the syntax has to go to functions from words to truth values. So true goes to the constant function true, false goes to the constant function false, easy. All the other connectives are interpreted pointwise. So for two functions from words to propositions, we give a new function from words to propositions, which takes the word and then returns the conjunction of f and g and them. So all the propositional connectives, very straightforward pointwise implementation. And the interesting stuff happens for the box and the diamond. If we have a function from words to propositions, we define another one in word v. The box is supposed to hold if the formula p holds in all accessible words. So then that's where the necessary intuition of box comes into play. Box then means it holds in all successors according to the accessibility relation. And diamond means it holds in some successor. So the diamond holds in world v if there is some successor world w in which the body of the diamond holds. This is now the usual definition of modal logic in terms of first order logic, except formalized logical framework extremely concisely. And if we added the proof theory to modal logic, we could of course continue here and do all the proofs. Gets a little annoying because formalizing the proof theory of modal logic in logical frameworks is itself a bit of an open problem. The natural reduction calculus of propositional logic cannot be inherited by modal logic. So you have to come up with some other calculus which makes things a bit more. But yeah, it's just tedious work. There's otherwise no kind of. And by the way, here we see now an example of a non-commutative diagram from propositional logic to this theory. We can now go in two ways. Propositional logic is included into the first order logic, which acts as a meta logic here, but it's also translated as part of the object logic of model. So because we're doing everything modularly, it's perfectly fine that we have two morphisms from propositional logic, because we're reusing it both to represent the target language and the object language of here. Also worth pointing out that this pattern is extremely common. We go from one logic to another logic, but in the codomain we actually have to add a theory in which we axiomatize a bunch of extra stuff that we need for the translation. In our case, the worlds and the accessibility. So that's very typically how these presentations look like. We have logic 1, logic 2. We're going to translate from here to here, but we're actually take some theory of logic 2, which formalizes a bunch of things we need, and then the morphism actually goes here. So one way to think of that is think of semantics. Think of logic 2 as a semantic framework like mathematics or set theory. Then this is the formalization of what a model is. In the case of modal logic, that's a cryptograph, so we have the theory of a cryptograph. In the case of first order logic, this is a set theory, this is first order logic, this is just a theory of a non-empty set. Or if we want categorical models, maybe this is ZFC, and this is the theory of a category, so that we can get a categorical model. So whatever basic structure we need in all models, that gets stuck in here. Don't have a good name for it. Sometimes I call it semantic prefix. Axiomatizing the semantics to have enough syntax to express. I'm going faster than planned. That's worrying because you don't ask any questions. So remember, you have to slow me down. Let's do another example of a translation. Here's the semantics of propositional logic in first order logic. So this is not just the inclusion. We already have an inclusion from it's typed again. we already have an inclusion here, of course, but that's going to be incidental. What we're actually interested in is the semantics that maps propositions to Booleans. So we extend this with a theory of Booleans, meaning we have bool TP. Remember, in type first or logic, we have things like TP colon type, TM, TP to type. We just declare the type of Booleans. And now our semantics of propositional logic is mapping propositions to T and bool. And then we have to map, for example, a conjunction to the usual operation on Booleans that does be formalize that one as well as a beginner example. Wait a little bit beyond, so it starts at type 4. Usual, S4 here, S for sorted, but it's the hard type version, where we have typed equality, typed universal quantification, typed existential, and all the stuff from propositional logic. And then formalize the type of Booleans. We have bool colon PP at PP for the true Boolean and FF for the false Boolean. Couple of axioms needed to get the Booleans right. At the very least, we need the inequality of true and false. And then we also want some extensionality axiom. We can skip that, but it's all here in the file. And then we can define something like if then else. When I do that. I put it here. So if then else takes proposition, the then branch, the else branch, and gives us back a term. So it's called the ternary operator in programming languages. It's a straightforward feature that we can add to classical typed logic. Probably should be classical because the if then else has this inherently classical idea that the Boolean is either this condition is either true or false. And we have the two defining axioms. If we can prove the condition, then if C then X else Y is equal to X. And if we can disprove it, then the whole thing is equal to Y. So it's just a logical feature. Doesn't even depend on Booleans. Just needs type equality in classical logic. But now I can define the theory PL model. That's the one I indicated here, the extension I need. It's not just Booleans. It has Booleans and if then else. So this is in turn built by combining the features of Booleans if then else. Essentially, the same intuition, it's an extension of the target logic with whatever we need to represent the models. And then we do the morphism. That's now this morphism mapping prop to T and bool. And it has to map proof of F now to a proof that F is equal to the true truth value. So that F goes to that F equal. Can be a bit confusing because now we have two levels of the propositions from first order logic and the Booleans as formalized in first order logic. And I think that we again have a non-commuting diagram because we can have two ways to map proposition and logic in here. But again, we see that we need this truth lifting, a top level step. We first translate propositions to Booleans and then lift them using the equality to the constant true. And then, for example, conjunction now. Oh, they're not doing the roots. So conjunction introduction. Well, let's see. Now the conjunction says, if X is true, then Y else false. That's the usual definition of the conjunction operator on Booleans. And then my conjunction introduction rule now takes a proof that F is equal to the constant true, a proof that G is equal to the constant true. And then we have to show that the entire if and else expression is equal to the constant true in that case. And of course, we do that by applying the rule for if and else. We know if the F is true, we can eliminate here, get the G, and then we know the G is true, so the whole thing is true. So it's basically just the application of trends and the if and else. Here I actually left the view partial. I think that's the only part of the atlas that currently doesn't compile. It's a harmless error because partial views are good as well, like partial morphisms work just fine. It's just that we're going to have kind of a runtime exception if we ever try to apply this to an expression that uses a constant that isn't mapped by the morphism. The MMT recovers gracefully for partial morphisms. It just issues a warning here in yellow that your morphism isn't total yet, and if you want to practice a bit, you can also add the other cases for the, well, for so other proof rules that we need to interpret. And if we do that, we have a kind of trivial looking semantics of propositional logic in terms of Booleans. But that's actually the starting point of a much bigger diagram. We can then, in the next step, extend this to first order logic. And then we can do the morphism that also maps first order logic in terms of Booleans. And then eventually here we can keep going higher order logic, and we can go to set theory. And then by chaining all these views, what we eventually end up with is the standard textbook semantics of first order logic, where we start in first order logic, and through the whole diagram, we end up in set theory. So the view I've shown you for propositional logic is just the way to start, where we have the simplest things. In particular, somewhere over here, then the p's have to become sets of set theory. Like the Booleans become just the set containing 0 and 1 on the set theory side. And then we are mapping our propositions to elements of the set 0, 1, which is exactly the typical semantics of propositions as truth values. So we need a little bit more than if and else to interpret the quantifiers. Probably doesn't work directly to here. We have to strengthen the language here. And then maybe we have to strengthen the logic a little bit as well. So for propositional logic, it's enough to have an if and else Booleans. So I formalize those quickly in type first for logic. When we interpret the quantifiers, we don't need all the complexity of set theory, but we need something in between the set theory. So we formalize that language, pick it, and then get to the morphism. So intuition is it's always cheap to go further to the right to the stronger logics. So we want to pick something that's as far to the left, like as close to the syntax as possible, but expressive enough to express the semantics. I would then be, I think, in the atlas, I'm mapping first order logic to some theory of higher order. We have time to quickly do the picture, and then that's it for today. The L model down here, then this gets translated to whole. Then we have the full model here. And then we can switch this one. And this morphism here induces a translation here by a push out. This commutes to the push out. So then we include this one here. And we have another morphism to set of C. And again, by a push out, and here we have that's the theory of a non-empty set. And eventually, all the way over is the semantics of first order. So more on that tomorrow. So I left tomorrow a bit open. I haven't fully prepared it yet. I'm going to mention a couple of side notes, a couple of limitations of frameworks, and fill in a couple of details that I haven't had time for. So if there's anything in particular you want to hear more about, just let me know in the break, and I can prepare more. Otherwise, see you tomorrow.